Hello everyone, welcome back. In this video, Gabby will be presenting some of the more advanced features of XSLT, mostly those that have to do with pull requests. So Gabby, over to you.
Thank you, Polly. Yes, so for this, I'm going to talk in this video about, in particular, a couple of features. I'm going to talk a bit about grouping and sorting, and then I'm going to talk about some other functions that you might use in the same sorts of contexts, and then we'll suggest an exercise that you can use, and in particular, if you're not following this as part of a specific workshop, but have just found this video on YouTube, then we'll have a link to where you can find some sample XML files on XSLT that you can start on and practice with to try out some of the things that we've talked about in this video and the previous videos in this series. So grouping and sorting, we saw, I think, in a previous video, for each used as a command in XSLT, and you remember that for each changes the context of the template and enables you to run multiple times to iterate over a particular element. So in this case, we're using for each not in the context of a particular element matched by a template, but we're doing this across the root of the document. So we're just saying, when you transform this document using XSLT, forget about what's inside it for now. Once you hit the root, then create a data table and do something for each word you find anywhere in the document. Okay, so anywhere in the document, / word, find for each word, if there are any, print inside this data table, print a datum, and print the value of that word. So we're not applying templates to the word, we're printing the value of the word and just getting it in plain text. That's relatively simple. That will just print a list of, do I have an example? Yeah, so here's an example of just the first half dozen or so from one of the sample XML files that you have, and this just prints each word as you come to them. It prints each word. It includes duplicates. It includes the words in in whatever mixed case they happen to be in, and anything else about the word. Just the text within that word. And that can be useful, but more useful if you want to do something like indexing would be to find ways to sort of filter some of those values out. So one way to do that is to use this element, which is very, very similar to for each, but for each group instead allows you to group your results by some value, some aspect of their value. And in this case, we're grouping by the content. That's what that dot means in there. And so again, we're finding all words, but we're grouping all words whose value is identical and only creating one datum for each unique word, rather than for every single instance of a word. So again, the first half dozen results we get here, and you notice now there's no duplication in here. Before there was duplication of a live uppercase and also a live lowercase, I think. But there's still duplication of alive and alive because this is case sensitive. Everything in XML and XSLT is case sensitive unless you tell it not to be. So again, what we've done is we've grouped together all the words by their content, and therefore we're not seeing multiple times a word that might occur multiple times if it's not unique. The other thing we can then do within this for each group is we can sort these words. So let's use this XSL sort element, and instead of seeing the words in the order in which they appear in the document, as here, we're seeing the words, and this again is just the first dozen or so instances in this document. You're seeing them in alphabetical order. Now, you'll notice one thing about this is that once you get beyond about halfway down that list, it suddenly doesn't look like alphabetical order anymore. You've gone from, alive, awakening, circulation, fine, that's alphabetical so far, still, the, and then back to A. What's going on there? Alphabetical order in Unicode, which is what XML is based on, is case sensitive again. So all uppercase letters come before all lowercase letters. So that's probably not what you want in an index unless unless uppercase words, were proper names and you wanted to separate them out, but there might be a better way to do that than just relying on mixed case sorting. So we'll try other things to get rid of that in a minute. But that's basically sorted the content by alphabetical order. The next thing we'll want is some functions that will enable us to tweak the content of this a little bit. One of those functions is the function lowercase. You've seen some of these functions before as we talked about XPath in earlier videos, but what lowercase does is it takes the string, in this case the string is a dot, so it's the content of the element, and it simply converts that entire element, that entire string, into lowercase. So if it was a lowercase word already, it's unchanged, but if it was all in uppercase, or if it had one uppercase letter in it, that will be transformed into the lowercase version of itself. Bear in mind that what we're doing here is we're grouping by the lowercase version of these words. We're not changing the words to lowercase. So when we're saying sort by the content is still in the original case. It's only the grouping that is done by the lowercase. The result of which is that we still get some words with uppercase and some with lowercase. We still get that strange thing going on with the sort, but we no longer have the word alive both in uppercase and lowercase as we did before, because the lowercase version has been grouped together with the uppercase version. And whether it's grouped with the uppercase version or whether it's grouped with the lowercase version depends entirely on which one turned up first in your list. So we've at least eliminated some. We're no longer getting alive and alive as if they were two separate words just because one of them has an uppercase A. If, however, now we sort by the current grouping key, and we also print the value of the current grouping key. The grouping key is this thing here in group by. It is the lowercase content. Then we get something slightly different. We're sorting it, not only, we're sorting the whole thing based on the lowercase value, and we're printing in the list the lowercase value. So we still haven't changed the content of the element to a lowercase word, but what we're seeing in the list is only the lowercase words, and all of them in alphabetical order, and all of them unique regardless of what case they were in originally. So we see alive only once, and again we're only seeing the first dozen, so we're not seeing any of the ones beginning with S or T, we're only seeing the first few in the list. So we have now successfully sorted them regardless of their case, and we're also printing them all in lowercase, and we've made them unique regardless of their case. So by combining lowercase and current grouping key, we've got rid of most of the weirdness that we saw in those earlier lists. Another really useful element, a function rather, for helping us to sort and filter words in this way is to use normalized space. What this does is if there are multiple spaces within or at the beginning and end of a string, it normalizes those away. In other words, multiple spaces within a string are reduced to a single space, and any spaces at the beginning or end of a string are stripped off altogether, assuming that they're unneeded. You'll remember from previous sessions that in XML, multiple spaces, whether they be spaces, tabs, new lines, etc., are redundant in XML and are in fact ignored. So one space is relevant, but multiple spaces are treated as a single space. That's the same principle behind normalized space. It gets rid of some of those extra spaces, which you may not want when doing things like sorting or indexing. So let's use a different example now. This is a sentence in an imaginary XML file, and you'll see that there are some words repeated in this sentence, and there are also, because of the haphazard way this XML file has been put together, there are spaces within the W tags and the word tags, and so some of these are going to be a bit of a mess. So if I say simply give me, if I were to just say give me each word in a datum, as we did before, there would be no grouping going on whatsoever in here. Each of these words would be unique, okay? Because the three thes, this one's in uppercase, this one's in lowercase with spaces before it, this one's in lowercase with spaces after it. So there would be no uniqueness in there at all. But if I run this thing, normalize space and lowercase on it, then all the words are turned into lowercase, all the spaces have been normalized away, and all the words are unique. Except for one. There's one weirdness in here. Why, I hear you ask, is the word cafe in there twice? This is something that you cannot see on the screen, and you probably couldn't see even if you tried to copy and paste it into a document. But in fact, this second E acute, on the second instance of cafe, is actually two Unicode characters. The first one is the Unicode character E acute. The second one is the Unicode character E followed by a combining acute accent, which looks identical and means exactly the same thing and should be in every sense absolutely identical, but when you're comparing two strings, they are not the same string. Can we deal with this, I hear you ask? We've got a function for that, normalize Unicode. So we grouping by the lowercase, then normalize all the spaces out, and then normalize the Unicode, and bingo, we've only got one cafe in our results. Okay, let's look at a few more text functions just to finish off. These are some of the things that we've looked at already, but I want to look at a couple of functions, in particular the function string and the function number. So let's look at, in the first instance on the left here, we've got a few examples of elements, the W element with and without n attributes, and we're simply testing. We're saying if this element, current context, has an n attribute, okay, and we'll see whether or not this is true in each of these cases. And you can see that this first W does not have an n attribute, but all of these do. Whether or not it's empty, what is or isn't inside it is irrelevant. If it has an n attribute, then it is true. So this test will run in all of these cases because there is some content in there. That might be what you want, but you might want that empty n elements be ignored. So one thing we can say is, we use the string function and say, if the n attribute of this element has the value of a string, that is to say, if there is anything in there that can be treated as a string, then go ahead and print this. And in that case, this one would turn up as false, and therefore the if would not happen. But in all the other cases, it would, because even just having a space in there still counts as a string. The next option I'm going to add, so that the one that was on the right has now moved to the left. The next one I'm going to say is I want to print this only if the n attribute contains a number. So that is to say, if when I try to read n as a number, it gives me a valid value. And in this case, the only one that is true is this one, where the value is 1. This one, with a space followed by 1, is a string, not a number. It cannot be treated as a number because it doesn't know how to get rid of that 1. Now, you can probably imagine we could normalize space as we saw in the earlier examples, and we could normalizing space would allow this one to be treated as a null string, and it would allow this one to be treated as a number. So we could do various things on that, but that's just for this example. The next function I want to talk about is the substring function. This is where you say, give me a particular substring of whatever value you've got. And most often you wouldn't put a string in this function, you'd put something like an attribute or some other XPath pointer to get some value. And so you'd say, go to the n attribute, and the n attribute happens to contain the word Antioch, and give me the substring starting at the first letter and that is one letter long, one character long. So this is the first character. And indeed, it gives you an A. This says starting at the first character and continuing for 3 characters, so A and T. This says starting at the third character and continuing for 2 characters, so it just gives you TI. And if you want to say you don't necessarily want to say how many characters to continue for, but to continue until the end of the string. You can omit the second value there and simply say starting at the fourth character, and the rest of the string is the substring. So there, from the fourth character onwards, you get the eoc there. So that's how substring works as a function. Substring is not a yes/no function. It's not saying if substring. It's saying, give me back and print the value of the fourth character onwards as a substring. Likewise, translate. This is a really useful one that will take a string, and again, you're more likely to want to put an attribute value or a value of an element in the first part of this function, but and you say find all instances of, and this is the second argument. The first argument is what you're performing this translation on. The second argument is say find me all instances of, and the third argument is and replace them with. Okay, and so this first one is saying find all instances of uppercase A and replace them with an uppercase Z. Why you would want to do that, don't know, but you end up with Zntioch. This is saying find all instances of the vowels A, E, I, O, U and replace them with the numbers 1, 2, 3, 4, 5. Only in lowercase, I should have said. And so it leaves the A alone, but the I and the O in there get replaced with 3 and 4, respectively. Again, don't know why you would want to do any of these things, but this is just to demonstrate how the translate function works. In this case, we're saying I want to replace any of the letters C, H, I, N, O, or T, printed in alphabetical order for some reason, any of those lowercase letters with the same letter in uppercase. Now that happens to be all of the letters in the word Antioch, and so it just turns the whole of the word Antioch into uppercase, all except for the A, which is already in uppercase. And in the fifth example, we're saying take the word in this string, take any vowel in uppercase or lowercase and replace them with. Now this string is not the same length as these. In these cases, the strings were always the same length of the second and third arguments. In this case, the third argument is shorter. It's infinitely shorter, in fact. And if it's shorter, anything beyond the length of the second string is treated as a null. In other words, replace any uppercase vowel or lowercase vowel with nothing. So it's now just printing only the consonants in the word Antioch. So you're just left with nch. So that's how translate work. You can convert a letter to another letter, or you can drop that character altogether from the list. And that's all very well if you know what it is you want to replace, of course. So a couple of test functions now. These are functions where you're asking a question, is it the case that, and the answer you'll get is yes or no. Rather, the answer you'll get is true or false. But so in this case, we have a, and so the first Boolean example we have is not. Okay, so we have a W tag with an N attribute containing 33. And I'm saying if test equals, so is there an @n on this? Is there an n attribute on there? Yes, there is. So the answer is true. Second one, is there not an @n attribute on here? Well, there is an @n, so there is not an @n, therefore it is false. Double negatives make that confusing, but so it is false. Is there not a next attribute on here? Well, I don't see a next attribute on here, no. So it is true that there is not a next attribute on here. Is the n attribute greater than 30? Yes, it is. It's 33. Is it not the case that the n attribute is greater than 40? Yes, it is not the case that it is greater than 40. So the answer is again true. So just as logic can be mind-boggling, these sometimes have to be thought through. Okay, this instance, this similar in some ways to substrings. This starts with function simply gives you an answer, yes or no, to does the string on the left start with the character on the right? And again, it makes more sense for this to be, for example, an attribute value on the left, so that you're comparing it against other things, or a variable or something like that. But just to show you how these work, just using two strings, does Berenike start with B? Yes. Does Berenike start with bear? Yes. Does Berenike start with nothing? Well, technically, the 0th character of Berenike is nothing, so yes. It is. We're not giving you a letter that Berenike does not start with. Let's put it that way. Does Berenike start with ere? No, it does not. Does Berenike start with bear? Why is that one false? Because there's a space snuck into the beginning of that opening string, and therefore it doesn't. It begins with space bear, and that's not what we're given. So that answer there is false. Okay, similar to, and now you're doing the same sort of thing, but matches is much more sophisticated because it enables you to use regular expressions. And we've mentioned regular expressions before, but we haven't attempted to teach them. So I suggest you go away and learn a bit about regular expressions. It's very easy to find if you haven't come across them before. But there's some really useful rules in here. So this is just simply saying, if you search for the second argument in the first argument, will you find, using regular expressions, will you find it? So if you search for a capital A in Artemisia, which is the lemma over here, will you find anything? Yes, you will. You will find one capital A. If you search for a lowercase a, will you find anything? Yes, you will. You'll find a lowercase a here at the end as well. If you search for what does that curly brace mean? The second instance of any vowel, is that what that means? Sorry, Polly, help me. My brain suddenly melted. Yes, so it's saying if you find any vowel occurring a second time, so square bracket A to U is any vowel, and the curly braces meaning the second time that occurs, I think.
Yeah, I think this is what that is. Suddenly not sure myself.
So capital A doesn't occur twice, E doesn't occur twice, but I does occur twice. So yes, it's true. It's found two I's in there. This one, do you find any vowel the third time? No. No vowel occurs 3 times in that word.
Yep, that's exactly right.
Yep. Cool, thank you. So this one is saying, will you find, if I search for capital A, any number of other characters that I don't want to specify, followed by lowercase a, will I find anything? Yes, I will. I'll find the entire string, in fact, from the beginning to the end. If I search for capital A, followed by any number of other characters, followed by a digit, will I find it? Well, there are no digits in there, so no, you won't. So that's just regular expressions on there. So matches is really useful if you want to run this sort of test across things. Only give me back those lemmata that contain a digit. Only give me back those lemmata that have each vowel, at least one vowel turns up 3 times or more, etc. So that was the exercise. You may want to go back and review some of that a little bit. That was the tutorial, rather. You may want to go back and review some of those. And of course, there are other places you may want if you want to go and find out more about regular expressions and so forth. But for the exercise here, we want to do a bit of what we call pull processing. So rather than running through an entire XML file with and in document order, and whenever you find a particular element, see whether you can do something with it, as we did with the first exercise using push processing. In this exercise, we're going to run a style sheet which creates a table or a list of some kind, pulling information out of a complex XML file and ignoring everything else in that file. As I say, if you're not at the workshop that we're running here in London, you can pull down a zip file from this link, which will give you a few example XML files and XSLT files that you can start playing with. The XSLT files are essentially empty, but they give you a very little output, but they're a basis on which you can build to get more output. And so start with, for example, you can do any exercise, and you really want to sort of try this for yourself, but for an initial exercise, start with the bad Hamlet XML file, and starting from the existing style sheets which we've given you, create yourself a new style sheet. Maybe take a copy of the Cruncher style sheet and create a new style sheet, and look for every cast item in there, right? Using for each on that, and see if you can answer the following questions. How many unique lines are there spoken by each cast member? Can you sort the lines spoken by each cast member alphabetically? And can you think of anything else you might want to do with it? So learn using some of the processes we've talked about in this video and in previous videos. What can you do on that on that file? So that's a sort of initial exercise, as it were. And of course, beyond that, you'll then want to try things out for things you actually want to do with your own XML files, and those can be discussed in the workshop if you're at a workshop, or elsewhere if you're not. Any other thoughts on that, Polly? I see you did actually ask me a question in the chat, and I didn't notice it.
Right, I was just wondering whether it would be useful to talk a little bit about these things that can be built up on these functions that you already showed. For example, you showed the substring function, but there are a bit more particular functions that could be used there, as the substring before and substring after. I mean, this is possibly useful only in certain circumstances. I use those a lot because I work with languages with morphemes that can be looked at like this, but I don't know if this would be useful for your students. And another function that I find really useful at this point when you introduce the Boolean ones is the contains ones. So
Contains,
I was wondering
right?
if you can
So
starts
with, you've got starts with, ends with, or contains, which can do which basically do similar things. Yeah. So if you say does Artemisia contain A, it's like that's it doesn't have to start with it. Does Artemisia contain T? The answer is yes. It doesn't start with, doesn't end with, but yes, it contains. And that's a lot simpler than matches, which is which involves regular expressions. Yeah, contains is substring before is slightly more interesting. Here's an example. I'm just going to put on the bottom of the screen in large letters a substring before instance. So what that's saying is find me everything in Antioch before the first instance of an I. And the answer to that is Ant. It's the same as substring 1 to 3, in fact, on the screen there. And if we change that to substring after, the answer to that would be och, I guess. And these are particularly useful in the sorts of cases you're talking about, Polly, where you have strings that maybe contain symbols as well as words. It's not so useful to say find me everything in this word up to and including the first I, but if you've got an attribute value which is, for example, the lemma followed by a hyphen followed by a bunch of other information, and you just want the lemma, you can say give me the substring before the first hyphen, and that gives you just that. So yeah, that sort of thing is quite useful to be able to play with that. Yeah. Thank you. And yet there are many other functions. I mean, I've only sort of scraped the surface here, but some of the reference material in XSLT will be useful. If you think to yourself, I wonder if there's a useful way to do, there probably is. And if you're lucky, it might be doing it with a function. If you're unlucky, you might have to write it yourself. But yeah. Great. Cool. Thanks very much, Polly.
Thank you, Gabby.
Cheers.